So I think today gonna be a short lecture. Okay, so we will discuss how to design a normal concrete mix. Okay, so this part of knowledge has been discussed in undergraduate level classes such as CE688. So if you have taken 375 with me or other professors, I think you probably have known this already. Okay, but not all of us coming from civil engineering background. So I will just repeat it because this is a very, very important skill to study concrete and how to design novel concrete. Okay. So factors in proportioning of quality concrete mix, there's many factors affecting the property of concrete, okay? For example, the workability. Seems like the density of the reinforcement, the spacing between the rebar will affect the requirement for the slump of the concrete. Okay. Consideration for durability, for example, if the concrete will expose to cold weather, so we need to worry about freeze-thaw damage in the concrete, then air entraining agent may be needed. Okay. If the concrete is in contact with high sulfate content from the soil underground, then we may use type 2 or type 5 cement. Okay. And also strength requirement. This is from the structure point of view, how strong you want your concrete to be. Okay. Appearance, the color of the concrete, the surface finish of the concrete. Okay. And also the cost of the materials, how much cement to use, how low the water cement ratio will be, so that will also be affected by the strength requirement. Okay. What type of aggregate you have? Okay. Most case, we're gonna use material locally. Okay. Importing material from other part of the world will be very expensive because for concrete we need a huge amount of raw materials. Okay. So most likely we'll use local aggregate, local cement if possible. Okay. And also admixtures such as flash, superplasticizer, fibers, and so on. Materials we can use in concrete, including cement, water, supplementary cementitious materials such as flash, slag, silica fume, okay. Water, of course, sand and coarse aggregate, and also chemical admixtures. Okay, for example, water reducing agent, air entraining agent, retarders or accelerators. Fibers sometimes is also added in concrete to enhance the performance, such as the toughness or the fracture strength, for example. Okay, so these are the possible materials we could use for concrete. And a concrete mix is defined with these mix properties. Okay. Some of them are already given. Some of them we need to decide during the mix design process. Okay. For example, the strength requirement typically is given from the structural engineer. So how strong you want the concrete to be. Then we're going to decide what is the water to cement ratio. Okay. The size of the aggregate property is already given, but we need to decide what is the volume for the aggregate. Air content, we need to decide that. The slump and the workability is depending on the type of job you put the concrete in. The water content is depending on the water to cement ratio and how much cement you need, which is also affected by requirement for slump. Okay. Then cementing materials content and type, what type of cement to use is depending on the exposure condition, such as sulfate, concern for sulfate attack, and also other mixtures. Okay. So the good thing is ACI, which is American Concrete Institute, has given very detailed guidance on how to decide these mix characteristics, okay, based on these tables. Okay, for high performance concrete and high strength concrete, we do not have a fixed mix design method. But however, for normal concrete, we have a very simple procedure to follow. Okay, for example, here is a table showing us how to decide the maximum water cement ratio and also the minimum strength requirement based on the exposure condition. Okay, for example, if there's no freeze-thaw concern, if there's no de-icing solution, no aggressive substances, then the maximum water cement ratio will be selected based on strength, workability requirements. Okay, and the minimum strength is selected for the structure requirement. If the concrete with low permeability or exposed to wet condition, then the maximum water cement ratio will be 0.5 and minimum strength will be 28 megapascal or 4,000 psi. Okay. If the concrete is exposed to freeze-thaw condition, in moist condition, then we're going to reduce the requirement, reduce the water cement ratio requirement to 0.45 and enhance the requirement for the strength to 31 megapascal. For corrosion protection, we're going to further reduce the water cement ratio. Okay, so the maximum water cement ratio will be 0.4, okay, or 35 megapascal. So the harsher, more severe exposure condition will use lower water cement ratio and higher strength requirement. Okay. And this table showing us the requirement for concrete exposed to sulfate condition. Okay, there are several different types of standard. Okay, so ASTM C150 is called standard specification for Portland cement. Okay, ASTM C1157 is performance-based specs for hydraulic cement. C150 is based on the requirement for different percentage of the compound. For example, the percentage requirement for calcium oxide. Okay. C1157 is based on performance. For example, the strength requirement or the setting time requirement. Okay. ASTM C595 is blended cement. Blended cement. So this table shows us, depending on the sulfate exposure, from negligible to moderate to severe. Okay. And here is the percentage of the sulfate in the soil percent by mass. Okay. And also the sulfate in water ppm. Okay. You should choose different type of cement. Okay. C150 is type 1, 2, 3, 4, 5. Okay. Type 1P is belong to C595. Okay. And type GU HE MS is from ASTM C1157. Okay. So basically 3 different standard. You could choose different type of cement depending on which standard you use. And also here is again the maximum water to cement ratio, depending on the exposure condition to sulfate, and also the minimum strength requirement. Okay. Here shows the name for the 3 cement standard. Okay. And the table on the top show the blended cement CEE688. Okay. So PM means Portland modified cement. The blend level is less than 15% of Portland materials, which is similar to type 2 cement in ASTM C150. Okay, so type 2 is moderate sulfate resistant cement. Okay. Type 1P is Portland materials. You can see the blend level from 15 to 40, which is corresponding to type 4 5 cement. Type 4 is low heat. Type 5 is a sulfate resistant cement. Okay, and you can just read from here. Okay, just in case you see the word GU, you can refer to these tables. You realize what does GU means, what does HE means. Okay, and what is corresponding type of cement in C150. And
is this sulfate concentration? It just depends on the kind of soil, or being close to the ocean or something like that affects it.
The sulfate most likely will come from the water or the soil. It could come from both. So if you have underground concrete structure pouring, you need to make sure the soil doesn't have too much sulfate, and then depending on the level, the percentage, you select different type of cement, and also the water cement ratio and the strength requirement. Okay, and also it could come in from the water.
Okay. Do we have soils like that here in Hawaii, or?
I'm not so sure. I do not think sulfate attack is a major concern in our environment. Okay, but when you have underground structure, it's always safe to measure the sulfate content, because you may have groundwater which may carry some sulfate. Okay. How to select the slump? Okay, it's based on this table. Okay, depending on the type of application. For example, reinforced foundation walls and footings, you could choose slump between 1 inch and 3 inch. Okay. Typically, you choose the higher end, the maximum value, okay, because it will make the concrete easier to mix. Okay. Beams and reinforced walls, you choose 4-inch slump. Okay. Pavement and slab 3 inch. So using this table, you can choose how many inch of slump for your concrete. So that's basically the first step when you design a concrete. Select the slump value based on the type of application. Okay. And then using the next table, based on the selected slump from the previous slides, and also the size of algae. So the size of algae is the maximum algae size in inch or millimeter. Okay. So that's the maximum size of the coarse algae. Okay. For example, if the slump is 4 inch and the size of your coarse is 3/4 inch, you're gonna choose the mixing water. So this is 205 kilogram per cubic meter of concrete, or 340 pound per cubic yard of concrete. And also here has 2 categories. the top 3 rows is non-air entrained concrete. The bottom 3 is air entrained concrete. Okay. So for air entrained concrete, you can somehow reduce the amount of water requirement because when we entrain the air, the concrete will be easier to mix. So you need less amount of water to make the concrete workable. If the question does not tell you it is air entrained concrete, you just assume it is non-air entrained concrete. Okay. And then we choose how much air, the air content as a percentage by volume for the concrete. For example, 1% air content means for 1 cubic yard of concrete, 1% by volume is occupied by air. Okay. So that is based on whether the concrete is non-air entrained or air entrained, and also the exposure condition, okay, as well as the maximum size of aggregate. Okay. So based on maximum size of the coarse aggregate, exposure condition, we can choose the air percentage. Okay. And the next table showing us how to choose the water to cement ratio based on the strength requirement. Okay, this is megapascal and PSI. Again, based on if the concrete is air entrained or non-air entrained, okay, we can choose the water cement ratio. Okay. If the strength is somewhere in between, for example, 5,500 PSI, and then we should use linear interpolation to choose the water cement ratio. Okay. So we get a slump, then we choose the water content from previous table. Then using this table, we choose the water cement ratio, and based on that, we can calculate how much cement we need for the concrete. Okay. And then we should figure out how much aggregate we need. Okay, let's look at how much coarse aggregate we need. This table showing us how to choose the bulk volume of coarse aggregate. Okay, first of all, let's refresh what is bulk volume. Okay. The bulk volume is occupied by the aggregate, including the solid volume and also the interparticle space between the aggregate. Okay. Let me draw something on my iPad. Okay. So the bulk volume, remember, is including the volume of aggregate. So this is aggregate packed in the container. So bulk volume basically is the volume of the whole container, including the aggregate and also the interparticle space. Okay, so go back to that table. So depending on the maximum size of coarse aggregate, and also the fineness modulus. So this is property for the sand. Okay. So when we discuss the aggregate, we show how we can calculate the fundamental modulus of the sand. The higher number means the size of the sand is larger. Okay, so based on the fundamental modulus and also the size of the cores, we can choose the bulk volume of dry rounded coarse aggregate. Okay. Again, if the fundamental modulus is somewhere between these values, we use linear interpolation. Okay. So far we can calculate how much water is needed, how much cement based on the water content and the water cement ratio. Then using this table, we can calculate how much coarse aggregate is needed. Okay. And also we figure out the percentage of the air. Then the only remaining unknown will be how much sand is needed. Okay, if we do not consider admixtures. Okay, for normal concrete, we do not consider admixtures. Okay. All right. So these are the tables we needed when we design a normal concrete. Okay. So before we go into an example, let's discuss two popular methods we can use to design a concrete. The ACI method and the PCA method. Okay. So ACI again means American Concrete Institute, and PCA is Portland Cement Association. Okay, so these are the organizations for cement and concrete materials. Both methods, they use the same table. The table is coming from ACI Committee 211 and also Committee 318. Okay. And both methods can give suitable concrete mix. Results are pretty similar, of course, because they use the same table. Okay. Today we just present the ACI method, okay, because this is the most commonly used method, at least here in North America, and the table is developed by ACI. Okay, so let's have an example here. So mixed design example with using ACI method. So this is the question given us. We need to design a concrete for reinforced concrete footing. Okay. The size of coarse aggregate is 1.5 inch. Okay. The 28 strength requirement is 3,500 psi, and also tells us standard deviation of 300 psi. Okay. I'm going to discuss why we need this information. And here are the materials property of the raw materials, including cement, sand, and coarse. Okay, the density, the specific gravity. Okay. By the way, the density is simply calculated as the specific gravity of the materials times the density of water. For example, the density of cement, 196, is equal to the specific gravity times 62.4 pound per cubic foot, which is the density of water. Okay, and same thing for sand and coarse. The specific gravity is in saturated surface dry condition. Okay, because later on we're gonna adjust the moisture content. Okay, right. Finest modulus of the sand, dry rounded weight for the coarse, and also the moisture difference or moisture content as a percentage. Okay, and also the absorption capacity for the aggregate. Okay, so we'll use this information to design our concrete. Step number 1. Okay, so we select a slump based on the usage. The question tells us this is the reinforced concrete footing. Okay, so reinforced foundation, walls, and footing. Okay, so we choose the maximum size, 3 inch. Okay, so 3 inch of slump for the concrete. Step number 2, we choose the size of course. which is we don't have much choice. The question tells us the maximum size of liquid is 1.5 inch. So 1.5 inch for the second step. Okay. Step number 3, determine the mixing water content. The question doesn't tell us the concrete is air entrained or not air entrained. So we just assume it is not air entrained. Then based on a slump, the slump is chosen as 3 inch. Okay. So 3 inch of slump here. And also the size of course, 1.5 inch. Okay. So the water content will be 181 kilogram per cubic meter of concrete. Okay, so that is water content. And then air content. Also depending on the size of the course, 1.5 inch. Again, assume it is non-entrained concrete. So air percentage is 1%. It is 1% by volume of entrained air. Okay. That's air content. All right, the next step, we choose the water to cement ratio. Okay, so this step is a little bit complicated. Right, the question tells us the required strength of concrete is 3,500 psi, and also standard deviation of 300 psi. So what we should do is we use these two equations. Okay, depending on the standard deviation S. Okay, S is 300 psi. So if S is larger than 10% of the required strength, okay, so in our case, it is less than 10% of the I prime C. Okay, so if less than 10%, we just use I prime C plus 1.34 standard deviation. So that is required strength for the concrete, 3902 psi. Okay. If the standard deviation is larger than 10% of I prime C, then we should use the higher value of these two equations. Okay, so F prime CR. So CR means required compressive strength is equal to I prime C plus 1.34 times standard deviation. Okay, the higher value of these two equations. Okay. Then why we have this equation? So basically, we want to ensure if we assume the strength of the concrete follow normal distribution, using this equation, we'll make sure 90% of the time the concrete mix will be stronger than the specific strength. Okay, the specific strength is 3,500. Okay, if the required strength is 3,900, we're gonna make sure 90% of the time the strength will be higher than the required strength of 3,500. Okay, so this is based on we assume the strength of the concrete follow a normal distribution. Okay. So required strength is 3,900, which is between 4,000 and 3,000. Okay, so we use linear interpolation. Okay, so we calculate our strength for concrete is 0.58. Again, we assume it is non-air entrained concrete. Okay, so in the previous step, we get 300 pounds of water. And now we get water cement ratio is 0.358. So the cement will be 300 divided by 0.58. So we need 517 pounds of cement. Okay. So questions for this step? Okay. All right. Then we're gonna estimate how much course aggregate is needed, okay, using this table. All right. The finest modulus of the sand is given 2.8. So 2.8 is here. The size of the course is 1.5 inch. Okay. So we need 0.71. This is the bulk volume of dry rounded course aggregate. Okay. So we want to design our concrete for a unit volume, which is 1 cubic yard. So 1 cubic yard is 27 cubic feet. So the bulk volume is 0.71. So that tells us we need 19.17 cubic foot of dry rounded course aggregate. So remember that is the volume including the solid plus interparticle space. Okay. The condition, the moisture condition for the course aggregate is 100. So 100 pounds per cubic foot, it is dry rounded weight. So that means for 1 cubic foot of volume, you can put 100 pounds of dried coarse aggregate in that unit volume. Okay, so for 19.17 cubic feet, we need 19.17 times 100. So we need 1917 pounds of dried coarse aggregate. So this is dried coarse aggregate. Okay. Now when we design our concrete for sand and coarse aggregate, we need to give saturated surface dry condition. Okay. Why we need SSD? Because only under SSD condition, the aggregate will neither absorb moisture or give out moisture to the cement paste. Okay. Otherwise, the water cement ratio will change. Okay, so we need to calculate how much saturated surface dry aggregate we need. And now we know for oven dry condition, we need 1917 pounds. We need to do one more step. So 1917 times 1.013, which is 1 plus AC. AC is for absorption capacity. Okay, so that equation will translate oven dry aggregate into SSD condition. Okay. And here is why. Okay. Okay. So this is 1917 times 1 plus absorption capacity. Okay, so 1917 is dry rounded weight. That is weight of aggregate in oven dry condition. Okay, so times 1 plus AC. AC is absorption capacity, is defined by WSSD minus WOD divided by WOD. Okay, so we simplify this equation. It becomes WOD, so WOD plus WSSD minus WOD. Okay, so WOD offsets WOD, so this also has, so this is become WSSD. Okay, so 1917 times 1 plus AC will give us WSSD. Okay. So that is yeah. Okay. So 1917 times 1 plus AC give us 1936. So this is weight of the coarse aggregate in saturated surface dry condition. Question about this step. Okay, so this step and the previous step okay, could be a little confusing if it's the first time for you. Okay. And then of course we will do a moisture adjustment, okay, based on moisture condition of aggregate, which is also confusing. Okay, could be. So far we get the volume by water. So we need 300 pounds of water divided by the density of water, 62.4. So for 1 cubic yard of concrete, we have 4.81 cubic feet of water. Okay. So 517 pounds of cement divided by density of cement, which is given. So 2.64 cubic feet of cement. Gravel, the same thing. 1936 divided by 168 given. So 11.52 cubic feet of gravel. For air, the air is 1%, which is by volume. So 27 cubic feet times 1%. So air content is 0.27 cubic feet. So the total known volume will be these four added together. So 1924. Okay. So the volume displaced by sand will be the total volume minus all other materials combined together in volume. So the sand volume will be 7.76. The volume of sand times the density of sand, 162, which is also given. So this is how much sand is needed. Okay. Step number 9, adjust for aggregate moisture. Okay, so this step is important. Okay. The question tells us the moisture content for sand, 2.5%. For gravel, 0.5% positive. Okay, so positive means the moisture condition for the sand and gravel are bad. The moisture content could be negative. Negative means the moisture content is air dry. It's drier than SSD. That means it is better than SSD. Okay, so we're gonna adjust the moisture accordingly. Okay, in the beginning, it could be confusing. Okay, why we should do that? So this is what we get in SSD condition. The cement, it is always dry. We didn't do anything. We do not need to do anything for cement. Okay, we need 300 pounds of water. Okay, 1257 SSD sand and 1936 of SSD gravel. Okay, because the sand and gravel are wet, okay, and they can provide some of the actual water to cement. So that actually increase the water to cement ratio. Okay, if you do not adjust the moisture content. How much more moisture the sand and gravel can provide? It is 1257 times 2.5%. So 31 pounds of actual water can be provided by sand because the sand is in bad condition. Okay? And similarly, gravel can provide 10 pounds of actual water to the cement paste. Okay, so totally the aggregate provide 31 plus 10, 41 actual pound of water to cement. Okay, So, however, we still need to keep the water cement ratio unchanged, which means we need to keep the water content equal to 300 pounds. But because the sand and gravel provide 41 pounds of actual water, so the water we added should be 300 minus 41, which is equal to 259 pounds of water. Okay. Then how much sand we need? So we need 1257 of SSD sand. Okay. However, the sand is not in SSD. It never will be. It is in wet condition in our case. So how much wet sand we need? So it is equal to 1257 plus 31 pounds of actual water. So we need 1288 pounds of wet sand. Gravel we need 1936 plus the 10 pounds of moisture on the surface of gravel equal to 1946 of gravel. Okay, so we added the material's weight on the left side, 4010, must equal to the new material weight on the right side, 4010. Okay, if these two is not equal, does not equal, okay, something wrong with the moisture adjustment. Okay, you need to check. Okay, all right. Question about why we need to do the moisture adjustment, how and why we need to do that. Okay, so let me do one more things just to make sure everybody on the same page. Okay. Because again, if it's your first time, it could be confusing. Okay. So from mix design, the cement we need is 517. Okay. And water we need, that's water. So we need 300 pounds of water. Okay. All right. And for sand, we need 19 gravel. In SSD, we need 1936. And for sand, okay, we need 1257 SSD. Okay. However, the sand and gravel are not SSD, they are wet. They are wet. Okay. Then we're going to figure out how much moisture on the surface of aggregate. Okay. So that is done by WSSD times the moisture content. Okay. For gravel, will be 1936 times the moisture content, which is 0.005. Okay, so that is equal to 10 pounds. So that means for the wet gravel, it has 10 pounds of more water on the surface of the gravel. So 10 pounds over the SSD condition. And that 10 pounds will be equal to the added water. So this 10 pounds will go into the cement paste, essentially increase the water to cement ratio. Okay, so that's why we need to adjust the moisture content. For the sand, okay, for the sand is 1257 times moisture content 0.025, 2.5%. 31 pounds, sorry, 31 pounds. Okay, so that means, I don't know how to draw, it's on the surface of the sand. So we have 31 pounds of water over SSD. Okay, so this 31 pounds and 10 pounds from the wet sand and gravel will be counted as the 300 pounds of water you needed. Okay, so we need to keep the water cement ratio unchanged. Okay, so the real amount of water we added, okay, will be the 300 minus the 10 pounds from the gravel here, minus the 31 pounds from the sand. Okay, so 300 minus 10 minus 31, so this is 559 pounds of tap water. So, okay, the real amount of water is still 300 pounds. Okay, so the 300 pounds is coming from 259 from tap water, 10 pounds from the gravel. This is gravel. And 31 pounds from the sand. Okay, so we want to keep this 300 water unchanged, no matter what is moisture content. So that's why we need to do the adjustment. And finally, for the sand and gravel, okay, how much wet gravel we need? Remember, the gravel is wet. We need 1936 plus 10, so 1946 pounds of wet gravel. Okay, for sand, it will be 1257 plus 31 is 1288 pounds of wet sand. Okay. And this is how we do the adjustment. Okay. Again, the moisture content could be negative. If it's negative, then here will be minus. Okay, for example, if it's minus 2.5%, then the sand will be air dry. Okay, so it will absorb moisture from the cement paste. So it will be minus 31, and then the added water will be more. The 31 will be added to this 300 instead. Okay, so in the beginning, it could be confusing. We'll go back, try to do that yourself, and yeah, you will understand. Okay. All right. The last step is to make a trial batch. Then you measure the slump. Then you measure the air content and compare the measured slump and air content with the design slump and air content, and also measure the strength. If it has any difference, you will adjust the mix design accordingly. Okay. Okay. Yeah. Today, again, will be short. This is a short lecture. We discuss how to design a normal concrete. As you can see, we do not consider any admixtures, no chemical admixtures, no mineral admixtures, no fibers. Okay. Just normal concrete, cement, water, sand, and of course, everything. Okay.